All right. Hi, everyone. Welcome to the seminar. So I'm delighted to introduce Leah Jenks from the University of Chicago, where she is currently a recently started postdoc. But before that, she was doing her PhD at Brown University with Stephen Alexander, and has recently graduated from that, is now moved to Chicago. So Leah has done some really interesting work on higher spin fields and higher spin dark matter, which I thought was pretty interesting for this crowd. So I invited her to give a seminar, and that's what she's going to tell us about today. So thanks for being with us, Leah, and take it away.
All right, great. Thank you so much for the introduction, and thank you all so much for having me. I'm very excited to be here and tell you all about some of my recent and ongoing work about higher spin fields and dark matter and cosmology. And so everything I'm going to be talking about in this talk is done in collaboration with Stefan Alexander, Jim Gates, Konstantinos Katrolikos, and Evan McDonough, my really wonderful collaborators based on these three papers that I have listed here with the archive numbers. Okay, so just to give everybody a little bit of an overview of where we're going in this talk, as you can tell, I'm discussing higher spin fields, which are in fact a universal feature of the theory landscape. But have not been studied very much in the context of cosmology. So we want to think about taking this feature of the theory landscape and thinking about how we can learn about them and probe these types of objects in the context of cosmology. And so I'll do that specifically in two ways. So first, we'll talk about dark matter and this idea of higher spin dark matter. And I'll show that within a kind of minimal model, we can actually explain the dark matter relic density today with a generic higher spin dark matter model for a variety of masses and spins. And then I'll show how with such a model, one could potentially obtain a distinctive direct detection signature in which we could distinguish a higher spin dark matter particle from a normal kind of WIMP or scalar. And then lastly, if we have time, I'll talk a little bit about within the same framework, thinking about higher spin interactions and how we can probe them using the cosmic microwave background with the Cosmological Collider program and how we get some distinctive signatures there. Okay, so I'll go ahead and start with just the basics. What is a higher spin field? So in the standard model of particle physics that we all know and love, we have spin 1/2 fermions, and we have spin 0 and spin 1 bosons. And for including the graviton, we have a spin 2. And so generically, a higher spin particle is any spin that is larger than 2. So for a higher spin boson, it's going to be a spin integer s particle with spin greater than 2. And for a higher spin fermion, it's a spin s plus 1/2 particle where s is greater than 2. And that's what we generically mean by that. And so, as I mentioned, higher spin particles are a kind of generic feature of the theory landscape. And there's a lot of history that goes back quite a while with them. And so in particular, one of the things that people always think about when we talk about higher spins are these no-go theorems, notably from Coleman-Mandula and Weinberg, where there are limitations on, for example, long-range interactions of higher spin fields and conserved currents. And people, you might wonder if this is a problem when we're talking about these higher spins in the context of cosmology. And fortunately, we can, in fact, evade these no-go theorems if we consider a massive higher spin effective field theory. These no-go theorems are in particular for massless higher spins. So if we consider massive higher spins, we are all set. And then similarly, there's formulation if we consider an infinite tower of free higher spin fields in which we can evade these no-go theorems as well. And so these higher spins do appear all over in physics in kind of different ways. So in string theory, if we think about Regge trajectories for masses and spins, higher spins appear there. In nuclear physics, there can be higher spin baryon resonances. In condensed matter physics, people talk about kind of composite higher spin particles. And then also if we think about quantum extended objects like D branes or P-form electrodynamics, really those objects are all representative of higher spins as well, some object with more than 2 indices. So they appear kind of all over the place in these different areas and different forms. And so we want to think about them in cosmology. So in the context of cosmology, the current state of cosmology, denoted here by the CMB, is that lambda CDM does a great job predicting or matching the CMB observations to really incredible precision so far. This is with some cold dark matter and a cosmological constant. But unfortunately, there's still a lot of open questions, and we don't really know what the lambda or what the CDM actually is, even though this model is so great. So, 95% of the universe is made up of things we don't know. And in particular, the dark matter problem, which makes up about 30% of the energy density of the universe, is quite wide open. So I always like this figure here, which was made by Tim Tate from the University of California, which shows just kind of the plethora of dark matter models that people have considered. So there is really quite a span. And if we think about this in terms of the mass range of dark matter, so on the very light end of a dark matter candidate is the ultralight axion, so around maybe 10 to the minus 22 electron volts. The standard kind of WIMP is around a GeV to a TeV. And on the very high end, if you want to consider, compact objects like black holes as the dark matter, we can go up to, 10 to the 4 solar masses, for example. So this is about 90 orders of magnitude in mass where we have potential dark matter candidates. And that doesn't really help narrowing things down. This problem is really, really wide open. And as I mentioned, for the last many years, the WIMP has been kind of the leading paradigm. And in direct detection experiments, so far WIMPs have not been found. That parameter space is shrinking where that is possible. And so from a theory standpoint and from a model building standpoint, I think it's important to think about alternatives and different ways we can think about this problem to approach it. And that's what we're going to do with higher spins as dark matter. So I think about this kind of paradigm in the center of this Venn diagram. And this is the way it was kind of initially formulated, where on the one hand, we have higher spin particles, which can come from string theory, but also elsewhere in these different areas of physics, as I mentioned. And there's been a growing interest in higher spins in cosmology in the last few years. And then on the other hand, we have this super heavy dark matter paradigm, the WIMPzilla, if you will, where we have dark matter particles with masses that are heavier than Hubble. And this is the kind of WIMPzilla idea that gains popularity in the late 90s, early 2000s. And so what we are going to be considering is basically a supermassive higher spin dark matter particle. And I should also mention, right around the same time that we were thinking about this a couple of years ago now, there were several other groups that also put out papers on a similar idea of a higher spin dark matter particle right around the same time. So this is a topic that I think has been of growing interest in the community, and there's a lot of open work to do. Okay, so we are gonna. So one of the things that makes higher spins challenging to work with is that we don't actually have a full generic theory of higher spin particles where we can just kind of write down an action or a Lagrangian that is universally applicable. We actually only know how to deal with higher spins really in flat space and in de Sitter space. And so we are going to exploit some properties of de Sitter space and consider just this kind of limited case. So in de Sitter space, there are 3 unitary unitary irreducible representations of higher spin fields that correspond to the mass range of the particle. So we have the principal series, where m squared over h squared is larger than this s minus a half squared. And then we have the complementary series, where we have this kind of small band of masses that are constrained by the spin. And then we also have the discrete series, where here t is just some integer. And we're going to be focused mostly just on the principal series and the complementary series here. I should also say S is the spin here. So yeah, we're going to be focused on these particles in these two mass ranges. So if we take these higher spin particles into Sitter space, we can in fact write down equations of motion, which is very convenient. So here, this sigma is the higher spin field, lambda is the helicity state, s is the spin, as I said, and then eta here is just conformal time. So we can write down basically, a modified Klein-Gordon type equation for the higher spin field that is solved by this expression here, where a and z are just some prefactors, and then this h I mu is the Hankel function. And so from this solution, one can find the other solutions for the other helicity states via this recurrence relation here. And this was first found by Lee, Bauman, and Pimentel in 2016. So, okay, so from our higher spins into Sitter space, if we want to think about how we are going to produce this dark matter, there are obviously many different mechanisms for dark matter production. One can think about freeze in, freeze out, etc. But we are going to think about gravitational production of dark matter, again, keeping with this analogy to the WIMP-Zilla case. So the basic idea of gravitational particle production is that during inflation or in the early universe, we have fluctuations of some field, and when these fields reach some violation, some particular scale where adiabaticity is violated, we obtain particle production. So in a very, so this is a non-thermal particle production mechanism. It doesn't require any couplings to the standard model or anything like that. It's a very kind of minimal way to obtain dark matter in the early universe. And so in a very kind of minimal way, we can express that by these expressions on the right-hand side of my screen. So if we have some rho phi density of our field, we can characterize it by just some delta phi, the fluctuation of the field, integrated up to some kind of cutoff momentum k star. And if we translate that to our higher spin case, we find actually that the density of particles produced in the higher spin case is actually dominated by the lambda equals 0 helicity mode. So it's this sigma 0 SS is the only one that we care about. This makes sense if you think about, for example, particle production of spin 1 dark matter. It's always the longitudinal mode that is significantly dominant over the other helicity states. So this is kind of where the intuition for that comes from. And we again have this density of dark matter with this integral where here the sigma 0 SS is that mode function that I showed on the last slide. So I should also caveat here just to say that normally when people talk about gravitational particle production and non-thermal particle production during inflation in this way, we consider particle production during inflation and then also during reheating and the transition to a matter and radiation dominated phase of the universe. However, in this higher spin case, as I said before, we only actually know how to really express this problem in de Sitter space. And so we exploit the fact that during inflation itself, the universe is very nearly in de Sitter space, and today the universe is very nearly in de Sitter space, to just consider the particle production during inflation itself. So we can think about this as a lower bound on the amount of dark matter that's actually produced, because there presumably will be some production as well in the radiation and matter dominated phases. But because we don't have expressions for our higher spin particles in those regimes, we just consider our particle production ending at the end of inflation. So everything I'm about to show in terms of the relic density is a lower bound on what we could get. So we just, to recap, we calculate this particle production during inflation and then assume these particles essentially just redshift like matter to the current day. So
sorry to interrupt, but
yes.
Can I just ask quickly, is there a risk that you could, for some of the parameter space that you'll show, you could be overproducing dark matter, or do you not expect this additional production to be a large amount?
Yeah, so I anticipate that it would change the parameter space slightly, but as I'll show in the next few slides, the parameter space is very open, I suppose, and it's really not constrained. So even if we were to have significant more production in these other regimes, I don't think it would change kind of the overall parameter space too much.
Sorry, can I at this point ask probably a stupid question?
Yes,
so when we say production from gravitational production, so you're not writing a Lagrangian term or anything, right? I mean, I'm trying to understand, do you couple this like a square root G or something, or?
Yeah, so this is the kind of very minimal case of this. So normally in the gravitational production story, you do have a full kind of action that's coupled to square root G. This is a little bit of a toy model for that process.
Right. Okay. All right. Yeah. Thanks. Understood. Thank you.
Yeah. Good question. Any other questions at this point? Okay, great. Okay, so as I said, we could look at from this kind of minimal model of these fluctuations during inflation, we can calculate the relic density for these mass ranges. So first we consider the complementary series, which again is this region here, this kind of small band of masses. And this is denoted here with this pink band. So here we have S, and then the energy scale at the end of inflation is on the y-axis. And so the parameter space within this pink band is where we get the correct amount of dark matter today for this parameter. And so you'll see that it's pretty constraining in this case. We would require pretty low scale inflation, about 10 to the 4 GeV, and we can only get masses that go up to about S equals 10. So it's quite constraining. However, if we go up to this blue region, which is actually where the principal series is, we find that there's a much wider range of parameter space. So now this is almost the same plot where we again have the energy scale of inflation on the y-axis, and then the mass on the x-axis, and then each of these curves represents a discrete value of the spin. And so anywhere on each of these curves is a point in parameter space where we obtain the correct amount of dark matter. So here, this black curve and the black curve denotes the Planck mass, and the gray region is excluded because we don't want super Planckian or trans-Planckian particles. And I should also say that we've just shown up to S equals 8 for computational purposes. Solving the recurrence relations that I mentioned a few slides ago is quite computationally expensive. So going up to S equals 8 is kind of a limit of what we can do. But in principle, one can also imagine that each of these lines will, there will be more lines going out to higher and higher masses and higher spins, all the way out to 10 to the 18, where the gray region will exclude exclude anything higher. And so what we can see from here is that for a really, really wide range of masses, again, masses larger than h, and a really wide range of inflationary scales. So this is pretty model agnostic to what kind of inflation that you want to have. You can have high scale inflation, low scale inflation, whatever model you like. There is generally going to be some point in parameter space where you could get the correct relic density of the dark matter with this procedure. And so again, back to the question raised earlier, this will change slightly if you consider the full particle production past inflation as well, but this kind of general story does remain the same. Okay. So now that we have produced the dark matter, what do we do with it? So now I want to discuss how we might be able to distinguish a higher spin dark matter particle from a normal WIMP or anything else with direct detection. And so we're thinking about direct detection experiments like LZ or xenon, for example, where we have scattering with a dark matter particle and some standard model nucleus. And so we're specifically going to be interested in directional direct detection, which is kind of a specific a subset of direct detection, which takes into account the fact that the Earth is moving through the galactic halo. And so because of this, this preferred direction, because of the rotation in the halo, there's going to be some sort of preferred direction for nuclear recoil events. And so the quantity of interest that takes this into account is called the double differential recoil rate, which is the rate of dark matter events, this is R, as a function of the recoil energy and the angular distribution. So this is this effect takes into account the angular distribution of these recoil events in the following way. So here, this d sigma, dE, d omega is just the cross section. V is the dark matter, the average dark matter speed in the halo. And f of v is some velocity function, which we just take to be a Maxwellian velocity distribution. And then here also rho chi is the dark matter density, m chi is the mass, and then mn is just a standard model nucleus mass. So previous work by Catena et al. In 2019 had showed that one can actually tell apart spin half and spin 1 dark matter using this method. So this is just an example plot from their paper where they show spin a recoil, this double differential recoil rate as a function of the recoil angles. And you can see that there is a distinctive difference between the two. And they argued that you can tell these two types of interactions apart with this directional direct detection. So we took that result and extended it to higher spins for both bosons and fermions. So we consider both bosonic higher spin dark matter and fermionic higher spin dark matter. I should also mention here that when we think about the gravitational particle production story, in principle, this does also apply to fermions and fermionic higher spins. However, we did not actually calculate that the parameter space for the relic density in this case. The kind of expressions, the equations of motion for fermions, higher spin fermions in de Sitter space actually don't even exist. So in principle, one can imagine that the story will be very similar to the bosonic case, but I should also just make that caveat here. So here we assume that we have some bosonic higher spins and some fermionic higher spins that we want to look for in the context of some direct detection experiment. So we consider the following Lagrangian. So here lambda Lambda is just some coupling. Sigma S on the left is the higher spin boson. N is the standard model nucleus, and then we consider a mediator that is a spin 1 mediator. The diagram looks like this, and then very similarly for the fermions, we have some psi S, which is a spin S plus 1 fermion that again interacts with the standard model nucleus via some mediator. Okay, so we consider the following interactions, and then we look at the double differential recoil rate. So in order to be more sensitive to the spin, we actually consider a scenario in which there are polarized targets. So this is then sensitive to the spin of the standard model nucleus and the higher spin particle, or the spin of the dark matter. And so we consider this difference in the double differential recoil rate, where here this S vector is the spin polarization of the standard model nucleus. And so schematically, we find the following for this expression, given the interactions which I previously discussed. So this B and F just denotes bosons and fermions. And so there are a few things to note here. So first of all, is that we have a characteristic kind of momentum fall off that goes like Q to the 4S. So this is very strongly S dependent, also, of course, dependent on lambda. And then we also have an effect that does not appear in the spin 0 or spin 1 case, which is the appearance of these Legendre polynomials. So this SI is just the spin independent part. This is the same for spin 1 and spin half, but these Legendre polynomials also appear. So PS is just, the Legendre polynomial as a function of Q is the recoil momentum and P is the incoming dark matter momentum. P prime is then the outgoing dark matter momentum. So we have this characteristic angular dependence in this expression, and then we also have this momentum fall off. So interestingly, what we find when we actually numerically evaluate these integrals, so here I've just shown a representative example for spin 3 on the left and spin 5 halves on the right. So this is the most the next step from in the lowest higher spin that one can have. And so what you'll notice here is that, first of all, these are just normalized so that the maximum and minimum values are 1, because we are really interested in this angular dependence here first. And so you'll see that these two plots actually look very, very similar to the spin half and spin 1 plots that I showed earlier, where for the bosonic case, we have this one main feature around alpha is pi over 2. And then for the fermionic case, we kind of have 2 features in this angular space. And so what we actually find here, which was a little bit surprising to us, is that this type of angular behavior in this recoil rate is actually a universal feature for bosons and fermions, regardless of the spin. So our kind of hypothesis, what we think about that is that, we do have this additional Legendre polynomial dependence in the angular dependence of this expression. However, because it's an integrated effect and the fluctuations due to that are quite small, it unfortunately does get washed out. So you can't determine the spin just based on the angular features, but you can determine whether you have a fermion or a boson, and it could be higher spin or it could be not. But we find that this is actually a generic feature for all 4 higher spins for both bosons and fermions. And so we also looked at the recoil spectrum. So this is the recoil angle alpha, which is just basically the theta angle in the recoil as a function of the energy. Again, for spin 3 and spin 5 halves being representative of spin S and spin s and spin s plus a half. And so we can see, particularly at low energies, they do have different behavior in the recoil spectra. I should also say that these were shown at the energy of 5 keV is the recoil energy. So we can tell the difference between spin s and spin s plus a half, but is there any way to determine the actual spin? And so what we do notice is that I said also, in addition to the Legendre polynomial dependence, there is also this factor of Q over lambda to the 4s. So there's this overall scaling with the spin. And so in principle, what one could do, if you consider measuring the recoil spectrum at multiple different energies, you can compare them. Here, Q is just proportional to the recoil energy. Those can be compared and the spin can be extracted that way. So for example, I've shown here for, again, spin S and spin 3 and spin 5 halves, excuse me, for 3 different values of the recoil momentum, which again just corresponds to the energy. We've divided by some reference momentum here just to scale everything in a little bit more of an intuitive way. But we can see that obviously there is a characteristic scaling depending on what the momentum is. Or what the recoil energy is. So from this, one can work backwards. If you are able to measure, for example, 2 of these and determine what the difference is, one can figure out what the spin is. So just to kind of summarize here, with this double differential recoil rate, we have this characteristic momentum fall off and also characteristic Legendre dependence. So the Legendre dependence doesn't do much, but we do have a characteristic universal signature for spin S and spin S plus a half that follows from the spin 1 and spin 1 half case, kind of a nice continuity there. But we can also potentially determine the actual spin of the particle from this Q to the 4s momentum fall off. So there is some potential for these types of detection signatures here. Okay, so lastly here, I want to mention the connection between higher spin dark matter and supersymmetry. So as I mentioned at the very beginning of the talk, higher spins are abundant in many areas of physics. One of them is in supersymmetry, in particular in superstring theory. We have predicts an infinite tower of higher spin fields. And so there has been work considering kind of dark matter in the context of supersymmetry, for example, this nice paper that came out last year. And so we want to think about if we consider these higher spin particles and our higher spin dark matter in the context of supersymmetry, does that give us anything? And so what supersymmetry gives us actually is a spectrum of fields. So here Y is a super multiplet. So I'm not going to get too much into the details about the string theory aspects of this. But for this is called the Y equals S super multiplet, and it gives us a spin 1 S plus a half field, 2 spin S fields, and a spin S minus a half field. And then you can also consider the S plus a half super field or super multiplet, which gives an S plus 1, 2 S plus a halves, and a spin S. So we wouldn't just have one higher spin field, we would have this spectrum of them. So in the context of this direct detection story, we would not just have the signature from one higher spin field, but we would actually have this full expression where we would have some linear combination of this rate from a spin S and from a spin S plus a half and from a spin S plus 1. So we would have kind of a correlated signal here correlated signature of many of these fields, and which potentially would give us some indication of supersymmetry. Okay, so now I want to switch gears a little bit. And so we've talked about higher spins as dark matter. And I want to, with the remaining time, speak quickly about some other work thinking about higher spins in the context of cosmology. And this is in the context of the cosmological collider. And so this idea was first proposed back in 2010 by Chen and Wang, and then Arkani Hamed and Malda Sena, very notably. And the basic idea here is that, on Earth, we are only able to access up to so much energy in our particle colliders. In our terrestrial colliders, it's certain we are, pretty limited about what we can, in an engineering sense, obtain. However, the universe is nice, and the universe gives us this period of inflation, which potentially reaches energies of, if you want to consider high-scale inflation, of 10 to the 13 GeV. And so in this kind of framework, one thinks about inflation as a particle collider, and then figures out how, if you have interactions of some massive fields during inflation, they are imprinted on the non-gaussianity of the cosmic microwave background in a very particular way. And so by studying the non-gaussianity of the CMB, we can learn something about the particle content during inflation, and if there are any new particles which we might be interested in. So this is now not necessarily in the context of dark matter. This is just thinking about a higher spin field generically. And as I said, there has been growing interest in this in the last few years. So extending this cosmological collider formalism to higher spin bosons was first done by Lee, Bauman, and Pimentel in 2016. They calculated the full squeezed bispectrum. And so the basic idea here is that we have the following interaction, where here small lambda and big lambda are couplings. This zeta is the curvature perturbation during inflation, and then sigma is a higher spin field. And so we have these two interactions, which can be expressed by this diagram here on the right, where we have the curvature fluctuations interacting and the interaction of a higher spin boson. And so what these authors found is that if you consider the 3-point correlation function for this bosonic case, this is the one momentum leg goes to 0, so this is called the squeeze limit. We find the following. The kind of specific details of this are not super important, but the important things to notice are that there is this characteristic, again, Legendre polynomial dependence that is popping up in the same way as in the dark matter case. Here, delta is just the power spectrum, alpha is coupling. And then this curly I is the shape function, which is, again, not the specifics of that are not super important here for what we're thinking about. So this is the case for bosons. And so this is all done in the, I should also just say a technical note, the Schwinger-Keldysh formalism, where we think about kind of interacting fields in terms of correlation functions instead of like scattering amplitudes. And so we can calculate a correlation function of some particular operator W in the following way, given some interaction Hamiltonian. And so what we are going to do is, using this formalism and using the higher spin kind of bosonic discussion as a template, we want to now extend this to higher spin fermions, and then also tie this into this story of higher spin supersymmetry that I mentioned earlier. So the thing that we're going to be considering is this 3-point curvature 3-point function zeta. And so for a higher spin bosonic field, we consider the following, or sorry, excuse me, a higher spin fermionic field, we consider the following interaction Hamiltonians, where here this Chi is a spin 1/2 particle, zeta is a, again, this curvature perturbation, and then psi is the spin s plus 1/2 fermion. So these are the two interactions we consider. And then in analogy to the fermionic case, we can proceed in the same way, considering the following interactions shown on the left, corresponding to the diagram on the right. So now it's a loop diagram where we have some interaction with this spin 1/2 chi and then the higher spin fermion. And then we find a similar result here for the 3-point function, where this is proportional to, now it's not just a Legendre polynomial, but it's actually an associated Legendre polynomial. This PSM as a function of K1 and K3. And then this corresponds to an approximate non-gaussianity parameter down here. I should also say that in this study, we were interested in looking at the broad kind of angular dependence of the signal. So the exact form of the k-dependence of the shape function, for example, is in this proportionality sign, but we're mostly interested just in this angular dependence. And so in the same way, as we talked about dark matter in the context of supersymmetry, we can talk about supersymmetry at the cosmological collider, and how we might be able to do this same type of connection. So again, considering, for example, this s plus 1/2 supermultiplet, we have not only a higher spin fermionic field, but we also have a spin s plus 1 and a spin s. And so we obtain additional contributions to this 3-point function and therefore to the non-gaussianity. And so we see that we have one contribution that goes as a PS plus 1, one contribution that goes like a PS, and then one that goes like an associated Legendre polynomial, this PSM. And so you can think of this in our paper, we discuss this as being like SUSY rills. So a rill is, for example, on the moon, when you have kind of these like grooves that are due to perhaps when there used to be water on the moon or things like that, you get these kind of characteristic ridges, I suppose. And so this is a way that we would have some similar kind of characteristic angular dependent signature of supersymmetry in the CMB non-gaussianity. And I should say that this is, again, very analogous to what we were talking about in terms of the direct detection, where we, again, have this spectrum of fields, and we have these kind of correlated signatures from particles of various spin, instead of just having a particle with one spin, we have the spectrum. Okay, so lastly, I would just like to highlight some future directions. So as I said, this interest of higher spins in cosmology is a pretty young field that has only been around for a few years. So I think that there is significantly more work to do. So in the context of, for example, particle cosmology, one could think about not just direct detection signatures, but also indirect detection or collider signatures. To think about if higher spins might impact these processes in some sort of characteristic way. I think in the realm of gravitational physics, there's also interesting ways in which higher spins can contribute. So there's this idea of the gravitational collider that has been discussed recently, thinking about a scalar field around a black hole. So thinking about higher spins in that context. is certainly an interesting future direction. There's also been some work recently looking at higher spin compact objects. So thinking about like higher spin solitons and higher spin boson stars, things like that. Also thinking about, in analogy to the Cosmological Collider program, how we might be able to think about this imprint of higher spin interactions in the stochastic gravitational wave background and in the anisotropies of that, even though we expect that to be potentially a small signature. If we have these interactions during inflation, they may give rise to gravitational waves. And then in nuclear physics, one can think about higher spin isotopes, for example, in the context of direct detection, as well as composite higher spin particles, and exploring how, if we have not just a fundamental higher spin, but some sort of composite particle, how does that impact all of these things that I've talked about? And of course, there's always many other things that we haven't thought of yet, and directions to go in. So I will wrap it up there, and I'm very happy to take any more questions. Thank you so much for your time and attention.
Thank you very much. Yeah, thank you very much for that fascinating talk. Yeah, let's have some questions. Igor, did you have one? You have your camera on?
Yes, well, hi Leah. Well, I have the following question. So you started in the beginning of your talk, you spoke about high-spin fields in de Sitter space, but then you considered interaction of high-spin fields with standard model particles in the experiments of direct detection. But standard model particles are defined as a representation of Poincare group in flat space. Well, isn't this contradictory? In general, why do you really need high-spin fields in de Sitter space rather than flat space?
Oh, yeah. So great question. Thank you. So we think specifically about higher spins in de Sitter space in the context of the production mechanism. So because we want these particles to be produced during inflation, and we want them to be accessible now, in terms of that, the particle production mechanism, we want to think about them in de Sitter space. But you're exactly right that in terms of the direct detection story, we don't have to be so constrained with that. The fact that we're in flat space is okay. So yeah, that's an important clarification. Thank you.
Dipan?
Thanks.
Yeah. So coming back to higher spins again, presumably, I mean, unless you have a tower, this is some, well, I mean, I'm thinking of like a fundamental theory, like this is some effective theory with a cutoff, right? I mean, if I could write down a Lagrangian description, for example, I mean, unless you have a tower. And in principle, I can just take that cutoff to like whatever small value I want. I mean, there's nothing, unless I'm thinking of some UV completion or some sort, right? So if you're looking at like things like gravitational colliders, so what is it that I'm really trying to like measure here? Is it just the coupling or the cutoff? Like the imprints give you what fundamental quantity? That's my question, really.
Yeah, so in terms of the gravitational collider, so I should also mention, oh, sorry, you're saying the gravitational collider or the stochastic background?
Yeah, I mean, generally, I mean, okay, so gravitational collider is one such object.
Yeah.
Like if I want to measure something, right? I mean, is it like a theory where I'm trying to understand an like constraining a coupling or a cutoff? Because in principle, if I think of this as an effective theory, I mean, I could have taken this cutoff to some small number, right? I mean,
right,
this would have blown up or whatever.
Yeah, I think you can think about it in two different ways. So I think kind of from that kind of field theoretic standpoint, you can think about it in terms of, right, we would be aiming to constrain such like the coupling with these types of observations. And then on the other hand, thinking about how can we make predictions for higher spin particles generically, perhaps regardless of the coupling or the cutoff, that would be, observable predictions that would be distinguishing from other particles of lower spin. So I think, that there's a twofold kind of aim there. So one would be constraining the theory, but also looking for ways in which we could potentially search for observable signatures.
I see. Okay. All right. Thank you.
Chris, I think you were next.
Thanks. So I was wondering, because you spoke about the de Sitter case and then the flat space case, but what about the case when you're working out the non-gaussianities? Do you need to kind of, is that just a purely de Sitter case because it's non-gaussianities developed during inflation, or is there some non-gaussianities that could develop due to the interaction of the dark matter during the kind of radiation era leading up to the cosmic microwave background?
Yeah, so that's a really interesting question. So definitely in the case of the cosmological collider, we're just using the fact that these are interactions during inflation. So we just consider in de Sitter space. I haven't actually thought about the non-gaussianity from, for example, like radiation domination, but I think similarly, I think that's difficult to do because we don't have necessarily a coherent theory in that region, but presumably you can imagine that you would obtain some similar type of behavior. But so far, everything that's been shown is just from inflation itself. Thanks for the question.
Thanks.
I have a question.
Yeah, go ahead.
Okay. In your earlier page, you wrote down the Lagrangian for the higher spin particle. Does it have any the non-minimal coupling like Pauli Zeeman term?
Non-minimal couplings.
You only
I think
the higher derivative terms, right?
Yeah. So this is this one.
Right.
Correct. Yeah. So we just considered one particular kind of class of interaction where we do have these higher derivatives. Yeah, I should say that in principle, you could also have, all of the indices contracted. You could have different types of couplings. You could have these non-minimal couplings. We just made a choice in analogy to this previous work to consider interactions of this form where we do have, these higher derivative terms.
Yeah, I'm asking whether there's a Zeeman-like term between the higher spin particle and background electromagnetic field. Like magnetic field, and that may have less suppressed in momentum the interactions, like usual Zeeman term, be that magnetic moment, and the magnetic moment is proportional to the spin of this particle. So compared to a spin 1/2 or 1 that we have in standard model, it will have parametrically enhanced Zeeman interactions, right?
Yes. Yeah, that's a really good point. That's not something that we had thought about, but I think that would be really interesting to consider. I think it certainly could have that type of interaction. Yeah, I think you're right that might lead to other interesting effects.
Okay, and another question is, isn't it that if you have the higher spin field, even if it's massive, from the lesson we have from string theory, unless you have infinite towers of a higher spin, isn't it some problem like causality even at the level of effective field theory?
Right. So yeah, so string theory definitely does require that you have an infinite tower. So we just chose to focus on kind of single spins as a representative example because, calculating, infinite of these is a little challenging. So there's a little bit of, I think, a distinction between the kind of string theory motivation for this and then, in principle, the types of things that we're looking at. So definitely in string theory, you would need an infinite tower. But we kind of just take that as, I guess, an inspiration to think about, what can we say about an individual higher spin if we were to have a scenario in which we could have such an interaction.
I'm alluding it because that sounds a little bit worrisome, because as soon as we decide to introduce higher spin dark matter, then we should have infinite many species of it, and they will all contribute to the abundance of the primordial dark matter, and that will overclose the universe. All sorts of these issues will come back.
Right. Yeah. So, I mean, that's definitely a concern if we're thinking about kind of everything in terms of a full theory. As I mentioned, though, we're just kind of considering some type of minimal model to see what we can say about this. But there is presumably also, for example, in the dark matter case, a region of parameter space where you could, for example, have such an infinite tower, perhaps with like a different production mechanism where you could have lower masses. But these are all things we've been thinking about a little bit, but haven't pursued yet.
Okay, fair enough. Thank you.
Archil? Oh, you're muted.
Hi, Leah. Thank you for a very nice talk. Yeah, I think I may have the same question as Sojung Gray, but let me formulate it the following way. So my understanding, whenever I introduce the fields with the spin 1 and the higher, and quantize this, I always have the ghost, the negative norm states in the Hilbert space or Fock space. And that requires some kind of invariance, some kind of gauge invariance to be able to remove them. So what is the catch here? Or you have some towers and so on and so forth, like Sojung Gray is alluded in terms of causality, for example. So what is the catch here? I'm not quite sure why these interactions are consistent with not having those pathologies in the theory.
Yeah, I think that's certainly a good point. I think in this particular case, we wanted to think about this from more of a kind of observational standpoint, and think about, if you did have such a higher spin particle, what would this interaction look like in analogy to, like, for example, the spin 1 case. So I think, certainly if we want to think about this in terms of string theory and field theory, we would have to go through and, be very careful about ghosts in these things. But that's at the level of this study, we didn't kind of do that analysis.
Yeah, I think they're just considering an EFT with a cutoff in some sense, right? In general, you would generate
in EFT, you have already ghosts, so that's a problem.
Yeah, even at the level of Fierz-Pauli, you will have a ghost, right? I mean, if Fierz-Pauli with a Master will have a ghost.
Yeah, but I understand that's cosmological study. That's fair enough.
Yeah. So unless you're like in a string theoretic setup, so that would be the
Maybe I just want to make a comment. Just to back up the Leah's talk. We may just entertain imagining the universe. We all live in the D-brane in string theory context. And D-brane in string theory context, it's not just the massless gauge field, but there's infinite towers of open string, massive higher spin states. Of course, there's a string scale, which is very high, but that already gives sort of theoretical setup that everything is consistent with the higher spin. The catch is, as I said, there are infinite towers of higher spins, and that's something I don't have a good idea how to get away.
All right, so I think, well, we can, if the people dying to discuss that further, we can save it for a second. I just wanted to quickly jump in and ask some of the questions I had. So I had more sort of technical question about the direct detection case. I didn't quite follow when you introduced this particular event rate that you were plotting, because you weren't plotting just event rate, you were plotting a difference of two rates. And I think you mentioned you were assuming like a spin polarized target. Is that correct?
Yes.
So what is the direction of the spin that you're assuming in this case?
So we just assume it to be oriented either in the plus z-axis or minus z-axis.
Okay, and then what is the because I guess there's two relevant directions in the problem. There's like the spin direction and then also the dark matter wind.
Right.
Do you assume that they're aligned, or?
Not necessarily.
So there would be some kind of modulation to this as well.
Exactly.
Okay.
Yeah, when people talk about, like, for example, like annual modulation of, the WIMP wind and things like that. So in principle, we would also have that effect here.
Yeah. Okay. And what do you have is there a type of experiment that you had in mind that would have these spin polarized nuclei? Because I mean, in the typical directional detection experiments, like with gas and stuff, the spins that can all be randomly aligned. So was there some kind of a proposal that you were inspired by for this, or is this just sort of required to do this?
I think my understanding is that perhaps in like the next generation direct detection experiments, this might be something that they would be able to probe. So potentially kind of, future direct detection experiments with, like, xenon tanks, for example, could do this. But yeah, there's not one kind of specific current experiment that I think is able to find this. So this would be some future looking thing.
So if you just calculate, rather than do the difference of these two event rates, if you just calculate the event rate for and then averaging over random spin alignments, do you not have as pronounced a signal for do you not have a pronounced difference between the different spin cases?
Right. So I think in that case, for the bosonic and the fermionic case, you still get some difference, but it's emphasized when you have the spin polarized.
Yeah, I see. Okay, yeah. And then the other thing I wanted to ask is what are the actual direct detection constraints on the models? Do they exist? I mean, this sounded like kind of parameter space plot with a direct detection constraints. Is there something like that for these models, or has nobody done that?
Yeah, so that has not been done. That's kind of the next step that we want to take with this, is do this. This type of study, as I mentioned, was very, just phenomenological to kind of see what types of effects one could get. The next step is definitely to say, okay, if you have an actual experiment that does this, with the constraints from, xenon or LZ or what have you, whatever other detector, to see what the actual kind of forecasts would be. So we haven't done that yet, but that's something we're thinking about, certainly.
Great. All right. Well, let me